I would like to take you through a scientific voyage where you can see how a mere observation by botanists became an important problem of fundamental physics, and then how a genius solved the problem with his Midas touch and paved the pathway of 20th century physics. The story entitled as Brownian Motion, a journey towards reality of atoms and molecules. It was early quarter of 19th century. A British botanist Robert Brown that time was engaged in collecting specimens from the different parts of the world, especially to the Australian and Tasmanian coasts. Coming back in the month of June, July, and August, he was that time busy in analyzing different specimens under the lens of microscope. In that period, he observed an interesting phenomenon. Pollen grains, when suspended in water, show irregular, random, continuous motions under microscope. It was the same like movement of dust motes in a room observed in the sunbeam. Now the next question that came into Robert Brown's mind, whether the motion is only reserved for living plants. So in search of that, Brown studied some inanimate objects like rocks, volcanic gases, and even meteorites. After analyzing all of them, he concluded that extremely minute particles of solid matter, whether obtained from organic or inorganic substances, when suspended in pure water or in some other gas aqueous fluids, exhibit motions for which I am unable to account. So, the main observation of Brown was that this type of zigzag type of motions, irregular continuous motion, later termed as Brownian motion, is not restricted only to the living plants. It's actually observed for any types of particles. So from here, the problem turns out to be a problem of fundamental physics rather than of life sciences. However, there are some debate over the originality of the discovery of Brownian motion. Some people think that it was Robert Leeuwenhoek who first observed this type of motion. Anyway, the credit goes to Robert Brown. And in scientific community, there is a notion that the credit hardly goes to the original discoverer of the event. Now, after Robert Brown, several other investigators also worked on the problem, and mainly some salient features or characteristics of the motion has been discovered. The motion is continuous, external, irregular, and random. It is independent of mechanical vibration. The smaller the particle size, greater is the motion. Viscosity has a role to play. Lower the viscosity of the liquid, greater is the motion. The higher the temperature, greater is the motion. But however, there were no substantial improvement on the problem over 75 years. The main problem was that most of the investigators failed to find what to measure, which physical property have to measure, because this type of motion is irregular in nature. Then you have to find a physical property which is not random in nature. So most of the previous investigators, they failed to find what to measure. Now, during the whole 19th century, there was a burning debate regarding the reality of atoms and molecules. Although we know that Dalton has proposed his atomic theory at the early stage of 19th century, even there were Avogadro hypotheses, but however, the reality of atoms and molecules was not established that time. During that period, two laws of thermodynamics were discovered, and people were very much convinced about the axiomatic aspect of thermodynamics. some peoples like Boltzmann, Maxwell, they were not satisfied with the macroscopic interpretation of thermodynamics. They want to go beyond that. So through the statistical approach, they proposed kinetic theory of gases, where they have treated the gas molecules as a real particles. So there are conception of a reality of atoms and molecules in the mind of kinetic theorists. But people like Wilhelm Oswald, the famous German physical chemist, Einstein, physicists come philosophers, they didn't believe in the reality of atoms, and atoms were only mathematical construct to them. So there is a apparent clash between thermodynamics and kinetic theory, because in kinetic theory the motion of each gas molecules has been treated as a reversible one. That means it has the same probability of going to the right and to going to the left. But we know that from the second law of thermodynamics that there is irreversibility in nature. It was Ludwig Boltzmann who explained the apparent paradox between thermodynamics and kinetic theory. According to him, although the individual motion of molecules is reversible in nature, but the motion of a collection of molecules become irreversible. However, the concept of atoms and molecules and their reality has not established, and Boltzmann was severely attacked by the group of anti-atomists like Oswald and Einstein. Boltzmann feeling isolated, and due to acute depression he committed suicide. So that was a problem throughout the 19th century, whether the atoms and molecules are real entity or they are mere mathematical construct. So the stage was set for a genius to make a connection between the Brownian motion and the reality of atom and molecules through a theory. And then the year 1905 came, popularly known as miracle year, where a person who was that time working on the patent office of Bern actually published 5 papers in under physics. Out of them 3 are revolutionary. The first one was on special theory of relativity, the second one was on quantum theory of radiation, and the third one was related to the Brownian motion, and the title of the paper was on the movement of small particles suspended in a stationary liquid demanded by the molecular kinetic theory of heat. And we know that person was that time working in the patent office of Bern, Switzerland. The world know him as in the name of Albert Einstein. But very surprisingly, Einstein made no mention of the term Brownian motion in this paper, and he also explained the facts why he has not mentioned that. In the opening lines of the paper, he mentioned that it is possible that the movements to be discussed here are identical with the so-called Brownian molecular motion. However, the information available to me regarding the latter is so lacking in precision that I can form no judgment in the matter. So basically, Einstein was emphasizing on the lack of proper information regarding the Brownian motion. And as we have already said that during the last previous 75 years, there was no substantial improvement regarding the study of Brownian motion. During 1905, Einstein also published his dissertation work and that was on a new determination of molecular dimension. However, there are some stories regarding the Einstein dissertation work. At that time, Einstein was affiliated to ETH, Federal Institute of Technology, Zurich. He first submitted a dissertation to the University of Zurich because that time ETH, or Federal Institute of Technology, was not affiliated to offer degree. So most of the people, those are working in ETH, got their degree from University of Zurich. For that, they have to submit their dissertation to University of Zurich. So Einstein first submitted his dissertation, but the topic was different. The topic was on the molecular forces in liquids. But surprisingly, he had to withdraw it in the subsequent year. Now the question is why? Because that time, we know that theoretical science was not a very popular field. And apart from some universities of Germany, in most of the universities of Europe, there were hardly any school of theoretical physics. And most of the chair professors were experimental physicists. So there was somewhat reservation regarding the theoretical physics, and Einstein's dissertation paper on the molecular forces in liquids was a purely theoretical derivation. And in ETH that time there was a single chair professor post, and Professor Alfred Kleiner was an experimentalist. He was the chair professor of ETH that time. So Einstein contacted him and submitted his dissertation work under him, but Professor Kleiner was not very convinced regarding the theoretical supposition and his lack of experimental proof. So he advised Einstein to withdraw his thesis. Later in 1903, Einstein tried second time to submit his dissertation on the same topics, but again he failed to do so. So Einstein was that time very frustrated. He said, the whole comedy has become tiresome of me. After that, in 1905, he got his degree, but the topic was changed on a new determination of molecular dimension, and the examiner was, or supervisor was, experimentalist Alfred Kleiner. Here in this paper, he calculated the size of sugar molecule using hydrodynamic theory. So his paper on Brownian movement and his dissertation work are basically interrelated. Einstein's dissertation work was reviewed by his own supervisor Alfred Kleiner and H. Burkhardt, who was a mathematical professor of mathematical sciences of University of Zurich. They were very much praiseworthy about the Einstein's work, but the only objection was that the Einstein's dissertation was very short. It contained very few pages. However, they overlooked a significant calculation error in the dissertation, which Einstein later corrected in 1911. Now we will see how Einstein solved the problem of Brownian motion. Einstein realized that even though the movements of all the gas molecules are random, or suspended particles are random, there are some quantities we can measure that are not random. They are predictable and can be calculated. One such quantity is density, and which is related to diffusion coefficient. So due to irregular random motion of the particles suspended in a liquid, they tend to diffuse into the medium with time. So Einstein thought that diffusion coefficient has a role to play. Einstein calculated diffusion coefficient by two different ways, one from the concept of random work or random motion, and another from the already known field of osmotic pressure equation and Stokes law, that means hydrodynamic theory. Now in random work is a very important aspect of the field statistical thermodynamics, is like a motion of a drunken man. Although the man is in his drunken state is going here and there, but the net displacement is nearly zero. So Einstein first realized that it is not the displacement but the root mean square displacement to be measured. So by that way he inserted statistical concept in his derivation. So actually he calculated the root mean square displacement, popularly known as mean free path. So by these two equations, one is coming from the random motion and another coming from the osmotic pressure expression and Stokes law, d is equal to kt by 6 pi r. He combined the two and got an expression for the root mean square displacement. Here is a total derivation done by Einstein, d from random motion and d from osmotic pressure measurement. So ultimately Einstein got a expression del square is equal to RT by 3 eta pi NAR into T. And Einstein also emphasized that T, the time for measuring the motion, should not be too low. So the motion of suspended particles to be observed for a relatively longer time. Now, Marian Somolowski also derived the same equation but in a different way well before Einstein, but he didn't publish it. After observing the publication made by Einstein, he published its papers in 1906. So in that way Somolowski was a little bit unlucky. But however, the equation of Einstein was sometimes known as Einstein-Somolowski equation. Now there is time for precise measurement. At the end of the paper, Einstein wrote that it is hoped that some inquirer may succeed shortly in solving the problem suggested here, which is so important in connection with the theory of heat. From the expression of Einstein, one can calculate the R, that means the radius of the suspended particle. So Einstein in his dissertation work calculated the size of a sugar molecule. So if you can calculate the size of suspended particles, so it's actually proved the reality of atoms and molecules. So atoms and molecules did really exist can be proved by the Einstein's equation. But there were three main challenges: how to produce an emulsion of identical grains, because if you want to test your theory, so each of the suspended solutes must be of equal size, how to determine the mass of the grains, and how to determine the radius of the grains. So all these were a challenge to the experimentalist. And then Perrin, our famous physical chemist, did the experiment in 1909 using the expression of Einstein and Somolowski. He calculated Avogadro number from the Einstein's equation. For that purpose, he prepared a colloidal suspension with dispersed particles of equal size. He used suspension of gambos, a gum-like polymer, and use elaborate centrifugation technique to get the uniform size. Then he observed the movement of the particles with a camera lucida, means a microscope. He established the predicted square root variation of root mean square displacement with time as proposed by Einstein in his paper, and then he calculated the value of Avogadro number. By that way, he obtained a value of 6.25 into 10 to the power 23, very much close to the presently accepted value. After seeing these paper from Perrin and the value of Avogadro numbers, in a letter to Perrin, Einstein wrote that I did not believe that it was possible to study the Brownian motion with such a precision. So from here, the reality of atoms and molecules ultimately established. Because if you can calculate the radius of a suspended particle, so it proves that atoms and molecules does exist. But it was not that Perrin first calculated the Avogadro number. It was Lossmead who first calculated the Avogadro number from experimentation. But that number was numbers per unit volume, popularly known as Lossmead numbers. The name Avogadro number was given by Perrin. So, through the theoretical foundations made by Einstein and Perrin's experimental measurement, reality of atoms and molecules became definitely proved. Century-old debate came to an end. Anti-atomists like Oswald convinced and accepted the reality of atoms, but Boltzmann was no more then. His soul must have been pleased, and by that way a new field, statistical thermodynamics, evolved through the work of Einstein and Samolowsky. Here are some useful readings for you, some good papers, original papers from Einstein's, Perrin. You can go through it. Thank you all.